right, let's talk about acid-base reactions. They are really a double displacement. So as always, it's nice to be able to identify polyatomic ions. What polyatomic ions are here? And we got phosphate and hydroxide. What other ions are involved? Potassium and hydrogen. Complete, yeah, if you were on Alex doing the complete ionic, sorry, it's tedious, huh? So how do you know this is an acid? Acids typically have hydrogens on the left. How do you know this is a base? Because of the OH, yeah. And what do acids and bases form? We say they like to form a salt and some water. And that might help us out. What is the salt here? That's the water. Yeah, and this can help us with our, because then we can see hydroxide hooking up with a hydrogen ion and forming H2O. So if I was just going to name the salt, I would call it potassium phosphate. All right, so phosphate's going to lose its hydrogens. Hydroxide's going to lose its potassium. All right, so what's the formula for potassium phosphate? I don't need a parentheses around this. I got -3 and +1. Yeah, K3. There is a potassium phosphate. All right, now let's balance it. If you look at the guidelines, sometimes it says do hydrogen, oxygen kind of last, polyatomic ions as a whole. Many times it says choose a metal. What metal should I choose? Potassium, and I see 3 here. It's going to force me to write a 3 there. And if I think about my polyatomic ions as a whole, now I have 3 hydroxides. I'm going to just put a 3 there. Now, does it look balanced? It looks to me like it's balanced. I got 6 hydrogens on this side. This 3 and that 3 give me 6. 3 times 2 over there gives me 6. What about oxygen? I got 3 and 4 is 7. 4 and 3 is 7. 1 phosphorus, 1 phosphorus, 3 potassiums, 3 potassium. Any questions on this example? Now I used to like the screen because I could pull down the screen, give a talk, put the screen up and come back to this. So in Alex, if it says write the complete ionic equation, I'm gonna do that for fun because it's just fun. So everywhere I see an aqueous, I can imagine that being completely disassociated. So far, so good. Now here I see this L for liquid. It's the driving force with this reaction, just as a solid would drive a precipitation reaction. So now that I have this way, we can ask ourselves, what ions remain the same on each side of the arrow? Oh, I messed up. How many hydroxides do I have? There, I got 3. I got 3 hydroxides here. Do I have 3 hydroxides over here? No. What about phosphate? I have a phosphate there. I have a phosphate here. Here's a phosphate. Got 3 hydrogens. Do I got 3 hydrogens? No. What's left? Potassium, potassium. And so what is the essence of this reaction? Notice here I have spectator ions removed. And then if we really want to be particular about rules and regulations, we can divide both sides by 3 and get something that looks like this. What do I name this thing? Nobody's working ahead in Alex. And then this is called the net ionic. This thing here is called the complete ionic. What's the difference between the two? Only the things that change, right? So this is the heart of the chemistry. At this point in your studies, an acid-base chemistry is a proton and a hydroxide getting together to form water. Every acid-base reaction will be like this. So the net ionic equation has the spectator ions removed. What are the spectator ions? They're the ones just kind of hanging out, and they're not involved in the chemistry, so to speak, but they remain unchanged. Nothing happens to them. Any questions about this? Let's apply some of that knowledge to this equation here. What is the net ionic? So here we have a precipitation reaction. That's the driving force. Makes the reaction go to completion. So if I take the heart of the chemistry, which has got to be this, and throw it into reverse, that's got to be my net ionic. What are the spectator ions? Well, if I imagine taking that apart, whoops, and taking this apart, my spectator ions must be sodium and chloride. Sodium and chloride are spectator ions. And the net ionic has the sodium gone, it just has carbonate. The copper has chloride gone, it's just the copper, so copper and carbonate hook up. Looks like copper 2 carbonate. All right, so here we're on to something new. A molecular equation is an equation showing the complete neutral formulas of every compound in the reaction. So here's aqueous silver nitrate, aqueous sodium chloride. You mix them together, you get a white precipitate, and here's sodium nitrate. That is the molecular equation. And then, unfortunately, in the Alex homework, you have to write a complete ionic equation. You just saw me write one. So that's where you take this thing, if it's aqueous, you say, oh, that means it's dissociated, and it exists as ions in solution. So you can write Ag aqueous, nitrate aqueous, sodium cation aqueous, chloride anion aqueous. And then when you look at, and you possibly up here, you would just write all the species, then you'd look at your solubility rules, and you'd have to say, well, this has got to be aqueous. Most chlorides are soluble, except for the exceptions of mercury, lead, and silver. So then you write the S there. And then if you look at this, we can probably deduce the net ionic and the spectator ions. So we only have separated the aqueous things into ions. That's what this bullet point here means. Do not separate a solid or a liquid or a gaseous compound. So here's a solid, my acid-base example, we had the liquid. In the complete ionic equation, some of the ions in solution appear unchanged. You see them on both sides of the arrow. And we call these things spectator ions because they do not participate in the reaction. They're the people sitting in the bleachers, cheering or head planting, depending on what's going on. Now, what do you think the net ionic equation is? So here's the driving force. If I take and write AgCl solid and then an arrow and do it in reverse, I'm probably going to have Ag plus Cl goes to silver chloride. All right, to simplify the equation and to more clearly show what is happening, chemists like to emit spectator ions. And when we do that, what we have is called the net ionic equation. So here's the silver cation, chloride anion, find each other in solution, stick together due to their opposite charges, and slough off solvent and sink to the bottom as a precipitate. All right, can you define everything you've learned today so far? Define molecular equation. It's a chemical equation showing the complete neutral formulas for every compound in a reaction. I think this is what we normally deal with. The complete ionic equation is a chemical equation showing all of the species that are actually present in solution. So everything with an aqueous, we separate it. This is mainly used for conception and teaching, and it helps us identify spectator ions. And identifying the spectator ions helps us see the actual chemistry, and the actual chemistry is showed in the net ionic, an equation showing only the species that participate in the reaction. All good stuff here. Any questions? Double exchanges yielding water. And of course, sometimes to help you see it, you write water HOH, because when you do that, it becomes obvious that this H hooks up with a hydroxide. Turns out I learned this trick from a biologist at a Wyoming flycasters meeting many years ago. All right, and here you see the salt. So a lot of times I say salt and everyone thinks sodium chloride, but it could be potassium bromide, Could be magnesium sulfate. A salt can also be defined as taking the hydrogen of an acid and replacing it with a metal. So we also call an acid-base reaction a neutralization reaction. Generally form water and an ionic compound called a salt that usually remains dissolved in the solution. So every acid-base reaction is basically this reaction here. Here's the net ionic. A hydrogen ion, a hydroxide like to come together and form H2O. All right, how do you tell if you're dealing with an acid? It has, H over on the left-hand side. And so sometimes I point this out to students. Here's how we write ammonia. Here's how we write water. Sometimes we do things like that. And water is amphoteric and can behave as both an acid or a base. And so it's kind of nice to write protons there on the left. Now nobody writes ammonia this way. And that might imply it could be an acid. But yeah, all these, when you see hydrogen on the left, you know they're acids. And you should see that they're all hooked up with these ions that you should all know, like nitrate, NO3 minus charge, sulfate, 2 minus charge, perchlorate ion, -1 charge. How do you know these are bases? Yeah, they all have the hydroxide. And here's pretty much an Arrhenius acid base. This looks like a Lewis-Bronsted definition. I don't think we really teach those in this class, so we'll just move on. Gas evolution reaction. Just like the precipitates and the neutralizations, these are also a double exchange. So I like to focus on this one, because everybody, when they were a kid, they made a volcano with baking soda and vinegar. Everybody did that, not just me. You never did it? Oh, shame. Now some of these times, these can be a little tricky. Let's just do the baking soda and vinegar. Here is vinegar, the acetic acid. So HCH3, HO2. The baking soda, looks like I should have color-coded this. So hydrogen's gonna go away and sodium's gonna hook up with acetate. And if I put hydrogen where sodium was, I could write something like this. Oh man, that doesn't look too proper, does it? Got 2 of them, we'll use the subscript. So there you see the double replacement. So what you gotta realize is this is carbonic acid. How many of you like to read ingredient labels? So sometimes your soda, sometimes it says carbonated water, sometimes it will say carbonic acid. I imagine if you buy it at the health club, it says carbonated water, and if you buy it at the mini mart, it says carbonic acid. This sounds like a chemical, the other sounds like something normal, right? All right, this thing here can break down into water and CO2. So there's the fizzing. So a lot of these can do something like that. So here's H2SO3. It can break down into SO2. So at least 2 of 3, that looked like a G. Intermediate product, none. Well, most sulfides are insoluble. So over in the stockroom, we have a bottle of this. And you want to be careful with this, because if you get it next to some acid. So what do you know about hydrogen sulfide gas? Anybody work in the oil field? It's your second job. You ever go out in the field and you smell this chemical? They never told you? It's poisonous. It kills you the same way carbon monoxide kills you. So you got to watch out for that. So here we see examples. So I tell students, if you see sulfide, carbonate, anytime you see a carbonate, you're going to get carbon dioxide gas. Sulfide, you have the opportunity to make hydrogen sulfide gas. Things like this we do in the lab, and this pretty much stays in solution. Any questions on reactions that make gas? Carbon dioxide's the big one. And then H2SO4, SO2. How many of you have ever experienced SO2? You make a bunch of Easter eggs and you forget about them. Then after a while you smell this smell. What is that smell? That smell is this chemical species there. So when you balance a gas evolving reaction, especially the ones with the intermediate, you might balance it like this. So when I see this carbonate and I see this nitric acid, I know it's gonna fizz, just because that's my job. But you as the student, what you'd do is you'd say, oh, I see ions, I'm gonna do the hoedown, and you'd swap your ions around. Then you'd pull out your solubility rules and you would tell me they're all soluble, and you'd say, oh, you made ion soup, there's no reaction. So you might wanna write down no apparent reaction, but it is not a no apparent reaction. There is a reaction. So carbonic acid, if you think about your soda fizzing, this likes to turn into carbon dioxide and water. So you get this thing done this far, and then when you see this, you decompose it. And then you get some balanced equation that looks like this. We might say 2 sodiums, 2 sodiums. The hard thing might be how many oxygens. Here's 6, and 3 is 9 oxygens. Here's 6, 7, 8, 9. Or the other thing might be hydrogen, 2 hydrogens, 2 hydrogen. Oxidation-reduction reaction. What does that mean? It means the transfer of electrons, and you already know a little bit about this when we predict charges. When I say, oh, you have some magnesium metal, and you can write down Mg, and you normally don't write a charge, there I've written a 0. And what do metals like to do with their electrons? They like to get rid of them. Yeah, they share them with something else. So here we went from 0 to +2, and we say this is an increase in oxidation number, so we call this an oxidation. What might be a good example of a reduction? All right, here's elemental oxygen. It's a molecular compound, it's diatomic. What do nonmetals like to do? Gain electrons. How many electrons does this need? Notice I have a -2 charge over here. I'm gonna put 2 electrons over here. And so now I can imagine taking magnesium and oxygen. Oh, and look, Eric, you messed up. What is 2 times a -2? -4. Boy, you're getting your money's worth today. Possibly. If I take this equation and multiply through by 2, I can stack this equation on top of this equation, add them together, and to get that equation. So this is a good example of an oxidation-reduction reaction. If I put magnesium and oxygen together, I think you're going to do this in lab, in a crucible. So predicting charges from the periodic table, you're already familiar with nonmetals liking to gain electrons, metals liking to give up electrons. Fundamental definition of oxidation is the loss of electrons. A fundamental definition of reduction is a gain of electrons. Helpful mnemonics. Oil rig. Oxidation, it loses. Reduction, it gains. I always like Leo the lion goes grr. Loses electrons, oxidized, gains electrons, reduced. I had an undergraduate chemistry professor, and he wrote a song called Leo the Lion Goes Grr, and he'd sing it. And I should have paid attention. I just ad-lib and make something up. Leo the lion goes grr. Leo the lion goes grr.
Yes. It was great.
It's a different tune every time I do it. Different key. All right, these things have to be tied together. I always say it's like a cell. Can you have a cell without a buyer and a seller? You gotta have both. If something loses electrons, like the magnesium metal, then another substance like the O2 must gain electrons. But for now, you need to just simply identify redox reactions. If you take general chemistry, we have a whole chapter on it. It goes on forever and forever. So redox reactions are those in which a substance reacts with elemental oxygen, just like my magnesium and oxygen. A metal reacts with a nonmetal, More generally, one substance transfers electrons to other substances. So I think we might finally get to my favorite reaction, because most people are pyromaniacs, and that would be combustion reactions. Combustions are redox reaction. So I have a friend who's a firefighter, and he says fire needs three things: fuel, oxygen, and maybe heat. So the fuel is the reducing agent, the oxygen is the oxidizing agent. The heat normally just gets it going, and then it goes on spontaneously. Looks like a good place to end.